Okay, in this video I'll do this problem shown here, which starts off saying consider the relation R on the set of integers n, natural numbers. R is those ordered pairs of such that the least integer, this funny looking bracket with the step on the bottom but not on the top, is called the least integer of x. So that the least integer of x over 10 is equal to the least integer of y over 10. Okay, least integer means we round down towards minus infinity to the nearest integer. So 2 is equal to, least integer of 2 is 2, least integer of 2.1 is 2, least integer of 2 point anything is 2, least integer of 2.999 is 2 also. Okay, so write down and describe the equivalence classes of T. It is an equivalence relation. And I guess part A sort of assumes that. It says the equivalence classes of T. Is it an equivalence relation? Carefully justify your answer. It is. And so this is sort of what we've got here. T0 is 1 through 9. And that's because 1/10 rounds down to 0. 2/10 rounds down to 0. 3/10 rounds down to 0. I think T0 actually includes 0 also. Isn't 0 in the natural numbers? So we can say that. And up to 9, 9/10 rounds down to 0. But then when we hit 10, we have 10/10, which is 1, which rounds to 1. All the way up to 19 rounds to 1. So the elements in, boy, I gotta correct this. The elements in T0, that is T0, round down to 0. The elements in T1 round to 1, and the elements in TK round to K. Okay? And so 0 to 9, 10 to 19, 10K all the way up to 10K plus 9 when we go to K. And this isn't, so these are the equivalence classes, and they are consecutive integers taken 10 at a time. They do form a partition of the natural numbers, and therefore it is an equivalence class, an equivalence relation. Okay, and here I show you there's reflexive, symmetric, and transitive. Okay, and I just essentially am writing out the definitions here, and you can verify that on the details. So this is an equivalence relation. These are the equivalence classes. And in fact, we can use the theorem that an equivalence relation defines a partition of a set. The equivalence classes of an equivalence relation define a partition of the set. And here we have a partition of the natural numbers into chunks of 10. And because that's a partition, that's enough to prove that the relation is an equivalence relation. Okay? So it's a very powerful theorem that I gave that relates equivalence relations and their equivalence classes to the partition of a set. And very often it's easier to prove that something partitions a set than it is to prove directly that it's an equivalence relation. So, hope that helps on this one.